Today I want to take a look at intermolecular forces. We've alluded to these in a few of our earlier programs. First off, let's look at the difference between what's meant by intramolecular and intermolecular forces. First of all, intramolecular meaning inside the molecule. If we consider a water molecule, the forces at play inside, or at least the bonding inside the molecule, deals with covalent bonds, the bonds between the hydrogen and the oxygen. Intermolecular is between molecules. In the case of the water molecules, here I've shown them with dashed lines. These represent the intermolecular forces. These are relatively weak in comparison with the strong covalent bonds that are inside the molecule. These weak intermolecular forces determine properties like melting point, boiling point, volatility, and hardness. There are three types of intermolecular forces we're going to deal with in this program: the London force and dipole-dipole attractions. These two together used to be called the van der Waals forces. And then finally, the last one, the hydrogen bonding, which is the strongest of the three. Let's start off with the weakest, the London force, sometimes also called the London dispersion force. It exists between all molecules. Consider, if you would, chlorine gas, chlorine bonded to chlorine, and here I'm showing a few of its many electrons. Those would be relatively evenly distributed throughout the molecule at some point in time. But due to the quantum nature of the atom, those electrons can take on different positions. And at some point in time, the electrons might be more at one end than another. This creates a condition that we call a temporary dipole. In this situation, we have a slightly negative and a slightly positive end to our chlorine molecule, which is usually completely neutral. This temporary dipole influences other chlorines that happen to be nearby. The electrons in the nearby chlorine molecule would also be pushed far to the right, causing a positive pole to form. Opposites attract, and this is the nature then of the London dispersion force, a very weak, temporary induced force that happens between molecules, all molecules. That force is increased with the size of our molecule. Larger molecules are more likely to have this uneven distribution of electrons. You can see it here as we move down the family of the halogens, from fluorine to iodine. Iodine, with the most electrons, has the strongest London force, as you can see from its very high melting point. In fact, it's a solid at room temperature. The shape of a molecule can also have some effect on the London dispersion force. The more closely the molecules compact together, the stronger the London dispersion force. Our second force are called dipole-dipole attractions. They exist between what are called polar molecules, and these tend to be a little bit stronger than our London force. Consider a polar molecule, HCl. There's an uneven distribution of electrons. Chlorine, with the greater electronegativity, pulls the electrons to its end of the molecule, creating a slightly negative and a slightly positive end of the molecule. This isn't temporary, this is a permanent dipole. It's always present. Another permanent dipole molecule that happens to be nearby will align itself so the opposite ends of the poles can thereby attract each other in what's called a dipole-dipole attraction. One of the skills we need to develop is to understand what is a polar molecule and what is a nonpolar molecule. Consider, if you will, BF3. Here I've shown you the dipoles that are present in the bonds between boron and fluorine. Fluorine, the most electronegative element, is going to pull the electrons towards its end. The shape of the molecule is a flat triangle, trigonal planar. Now, although this molecule has bonds that are polar, is the overall molecule polar? To do that, we add together each of the bond dipoles, much like adding together vectors. To do that, we add the vectors, tip to tail, and we can see in this case we've returned back from where we started. That means that overall, this molecule is not polar. There is no net dipole movement of electrons from one end to the other end of the molecule. So it's what we would also call a nonpolar molecule. It wouldn't have dipole-dipole attractions and would therefore have to rely upon only the London force. Here's another molecule with a similar number of atoms involved, nitrogen trifluoride. But what's different in this situation is the shape of our molecule. It's pyramidal in shape. with an unbonded pair of electrons at the top. Again, I've indicated the bond dipoles with the blue arrows, and we'll add those together. Again, adding them tip to tail. And we can see generally we get a downward movement or a downward movement of electrons. Thus, this molecule would be considered polar and therefore would have dipole-dipole attractions. We can also have a relatively weak attraction if we bring a polar molecule near a nonpolar molecule. It can induce or cause the nonpolar molecule to become polar for a short period of time. Finally, hydrogen bonding, the strongest of our three. This occurs whenever we have hydrogen bonded to nitrogen, oxygen, or fluorine. Consider, if you will, these two molecules at the side. Both of them have oxygen, both of them have hydrogen, but do they both have hydrogen bonding or are capable of hydrogen bonding? Remember, the hydrogen must be bonded directly to the oxygen, nitrogen, or fluorine. So our top molecule would be a candidate for hydrogen bonding, but the lower one would not. Even though it has both the elements, the oxygen and hydrogen are not bonded with each other. Now, the reason that the hydrogen bond exists comes from the high difference in electronegativity that exists between these three elements and hydrogen, creating a slightly positive hydrogen, and the other element becomes slightly negative. When another nearby molecule comes near, it will align itself, so the slightly positive hydrogen will be facing those unbonded pairs of electrons that exist at the slightly negative end of the other molecule. This creates the weak attraction that we call the hydrogen bond, the strongest of our three intermolecular forces. It's about 1/10 the strength of a covalent bond. Water and hydrogen bonding have sort of a special relationship. Here I've shown several water molecules and in fact the hydrogen bonding that forms between them. Water is capable of bonding with 4 other molecules by means of hydrogen bonding. That means that when it becomes a solid, as it does in ice, we get this nice orderly arrangement that we call ice with the tetrahedral arrangement. In liquid water, we might only form a couple of the bonds and as a result don't get the nice stacking pattern. What you will notice in the presence of ice, though, are holes or spaces. This is what causes ice to be less dense than water, why ice floats. As mentioned earlier, the intermolecular forces will have some effect on melting and boiling points. The stronger the intermolecular force, the higher the melting and boiling points. Let's consider these 3 for a moment. I'm going to provide their structures below. Let's take a look at whether or not the London force would exist. Well, first of all, we know that all molecules are capable of generating the London force. So all 3 of these would have London forces between neighboring molecules. What about dipole-dipole forces? Well, for that situation, I need to look at whether or not the molecules are polar or not. The first candidate is not. The difference in electronegativity between carbon and hydrogen is pretty small, and in fact, all of the bond bipoles would add together and cancel each other out in that symmetrical molecule. The other 2, however, are slightly polar, and as a result would be candidates for dipole-dipole interactions. And finally, hydrogen bonding. Well, only our last molecule would be capable of having hydrogen bonding. So as a result, I would expect the last molecule to have the highest boiling point, and the first one to have the lowest. Let's look now at solubility. Solubility is affected by the polar nature of the solvent and the solute. If both of them are polar, they can be attracted to each other. If both of them are nonpolar, then only the London dispersion force can attract them to each other. The rule we often say is like dissolves like. Polar will dissolve in polar, and nonpolar will dissolve in nonpolar. Again, let's look at 3 different molecules here. And again, I've provided their structures, as well as indicated which ones have dipoles. Our first candidate is a nonpolar molecule. That means if we were to place this in water, which is polar, there would be no attraction, or very little attraction that would exist in this situation. As a result, I would expect it to be the least soluble of my substances. Both of these molecules are polar, and both of them are also capable of forming hydrogen bonds with water. Let's take a look at that. Here's the molecule shown on the left, and that OH combination at the end is capable of bonding with 3 water molecules. So as a result, there's a considerable amount of attraction between these molecules and water. So I would expect them both to exhibit some solubility with polar water. But I also need to consider this large nonpolar section of this last molecule. That would reduce its solubility somewhat. So now ranking the last two, I would make the CH3CH2OH, also called ethanol, that would be probably the most polar, and that's the most soluble. And the second one would fall in between. So that's a quick look at our intermolecular forces. I hope that's helped out with some clarity in some earlier programs. Questions are always welcome. Thanks again for watching.